I'm Greg Osuri, the founder of Akash Network, a distributed systems engineer and a long-term open source believer. Today isn't another model architecture talk. It's about infrastructure behind these models. It's about a very specific claim that distributing computing architectures can help solve AI's energy crisis. Distributed computing architectures can help solve AI energy crisis while expanding access to compute to the entire PyTorch community. In my testimony I've given before Congress, I made one claim. AI is becoming the substrate of civilization, and AI is the foundation layer. But foundations only work if the power stays on. We are approaching an energy bottleneck that could limit who gets to build, ship, and even run AI. We can fix that by distributing where, when, and how we compute. So here's what we're going to talk about in the next 20 minutes. First, we begin with quantifying the energy reality, why centralized hyperscalers are hitting hard limits, what a distributed architecture looks like concretely for PyTorch training, the algorithmic breakthroughs, basically low communications and asynchronous fault tolerance training that make the internet a viable cluster, empirical case studies, how Akash, News, Jensen, and what the numbers actually say, and a buildable architecture and a call to action for the PyTorch developers. Let's anchor on data. The US Department of Energy report estimates US data centers consumed about 176 terawatt hours in 2023, about 4.4% of US electricity. By 2028, the range is 325 to 580 terawatt hours, or 6.7% to 12% of US electricity. At the high end, that's 1 in 8 watts on the grid going to data centers. The curve isn't linear. It's steepening, driven in large part by accelerator-based AI. This isn't abstract. If power doesn't arrive at the plug, your job wouldn't schedule, your training run wouldn't start, and your inference fleet will throttle. That's the reality our infrastructure teams are living with right now. Analysts are warning by 2026, 40% of AI data centers could be stuck waiting for power, even as some facilities spin up diesel at peak to stay online. Power shortages and costs can throttle next-gen models regardless of algorithmic progress. We must treat energy as first-class constraint in our training stack. Environmentally and economically, the math compounds. On current trajectories, global data center electricity could approach about 945 terawatt hours by 2030. And the cost profiles are massive. Frontier training and large-scale inference are already multi-billion-dollar line items. If compute access is functionally gated by energy, we risk centralization by default. Only a few players can pay the bill. So here's a constraint in one line I stand by. AI demand is exponential. Our energy response can't be linear. We need architectures that use energy smarter, spreading load, lifting utilization, and co-locating compute with abundant, cheaper renewables. That requires us to rethink the where and how of training, not just the what. Centralized hyperscalers gave us incredible economies of scale, but three hard ceilings are its current limitations. And now are very, very obvious. So first is geographical power constraints. Interconnect queues, substation limits, and community caps, adding another 100 megawatt site isn't always possible or fast, and diminishing parallel speedups, right? Ultra-large, tightly coupled, training hits synchronization and communication walls. Idle bubbles dominate. And third, we have underutilization. Even very large estates rarely keep accelerators near 100% useful work. Waiting on data or coordination burns watts without progress. If energy is scarce, idle watts are unaffordable. An alternative is thousands of nodes. Small data centers, campuses, labs, and individual providers cooperating over the internet to train one model. That is not science fiction. We've seen precedent at internet scale. Folding at home volunteers once peaked around 2.4 exaflops, outpacing the top supercomputer at that time. With the right algorithms and verification, we can turn the internet itself into a capable, resilient training fabric for PyTorch jobs. So what do we get? Higher utilization. Keep powered GPUs doing useful work, not waiting to turn idle gaps into gradient steps. Grid-friendly dispersion. Spread loads across many regions, placing compute where renewables are cheap and abundant. And third is resilience by design. No single points of failure. Jobs adapt as nodes come and go. And democratize access. Anyone with hardware can contribute, and anyone can rent via open marketplaces. This aligns with the open source values baked into PyTorch culture. For energy, dispersion plus utilization equals more work per watt. We tried WAN training a decade ago and bounced off the walls high latency, random dropouts, widely heterogeneous nodes. But the last 2 years delivered breakthroughs that flipped the calculus. Low communication training, asynchronous fault-tolerant swarms, cryptographic verification, and incentive layers. Taken together, these make training across internet practical for serious models. Two examples you can map to PyTorch today. Oops, my bad. So first is Dialog-Co. Distributed low communications. Instead of synchronizing every step, do large blocks of local updates. For example, hundreds of steps that sync infrequently. That's roughly a 500 times sync reduction with similar final accuracy. Implementation-wise, wrap your optimizer to checkpoint local steps and then exchange infrequent compressed deltas via a custom process group. News Research Distro, a WAN-aware optimizer stack that combined heavy compression and sparse exchange to cut per step bandwidth from 74.5 GB to 86 MB in one test, an approximate 857 times reduction with no significant accuracy loss. Think parameter space transforms. 1-bit signs for updates and sparsify top K or column-wise structures. Map this to a torch.distributor backend with quantization and structured sparsity hooks. The takeaway is trade bandwidth for local compute and smart compression. Your interconnect becomes good enough. And the second pillar is asynchronous updates. Don't wait for the slowest peer. Let fast nodes sprint ahead. Slow nodes contribute at their pace. Momentum corrections stabilize stale gradients. And dynamic swarm rerouting. If a node drops, shards reassign and training continues. No job restarts. Verification. Cryptographic spot checks to validate work with manageable overhead, enabling train-to-earn incentive models for untrusted nodes. Pluralis' swarm parallel with Nesterov accelerated gradient shows stable async training over heterogeneous links. Jensen's skip pipe keeps throughput under churn and verifies results with about 46% overhead while maintaining about 93% accuracy at 50% node dropout. That's remarkably robust envelope for real networks. In PyTorch terms, this looks like asynchronous parameter servers or peer meshes with fault-aware schedulers and verifiable update submission. On Akash, we run a decentralized GPU marketplace where independent providers bid to run your workloads via a reverse auction. Since enabling GPUs, the network has scaled from about 150 to about 1,000 plus GPUs, while sustaining roughly 54 to 55% average utilization across a very heterogeneous fleet. That's competitive with large clouds and far above typical on-prem. It means few idle watts and more useful gradient steps per kilowatt hour. Here's how it allocates without a central scheduler. Users post a containerized job spec, which is GPU type, memory, storage, and price ceiling. Providers bid. The lowest conforming bid wins the lease. The market continuously routes work to where the capacity is idle and priced right. An autonomous utilization machine. For PyTorch users, this is simply a different cluster API target. Your code doesn't need to change, your deployment does. A concrete decentralized trading milestone is Noose Research trained a 15 billion parameter LLM over the public internet on volunteer machines and donated instances in about 10 days and about 11,000 steps. Matching centralized run accuracy using WAN-aware optimizers. This demonstrates that with the right comms and async strategy, frontier class models can train beyond a single hyperscaler. Verification is a linchpin if you're playing with untrusted nodes. Jensen's on-chain workflow uses solvers, verifiers, and whistleblowers. Their protocol achieves about 46% verification overhead, not 10 times or 20 times, but still retains 93% accuracy under 50% churn thanks to fault-tolerant scheduling. You can operate a decentralized PyTorch training market where correct work pays, and provably so. So let's summarize what the data shows across projects. Utilization. Decentralized fleets can hit 50 to 60% sustainable utilization, and that's 3 times over many on-prem baselines. Accuracy. WAN-aware low-com runs show negligible accuracy deltas, typically under 1%, with 500 to 857 times less bandwidth. Scale. We've seen 10 billion to 32 billion parameter runs reach parity using mixed volunteer networks. And cost. Marketplace pricing plus idle capacity can materially undercut conventional cloud for many workloads. The net effect is more work per watt and wider access without sacrificing model quality. Now imagine scaling this with small modular data centers. Containerized racks on campuses, in offices or community sites parked next to solar, wind, or hydro. Compute rides on local clean energy, slashing transmission losses, soaking up daytime solar peaks, and spinning down at night. Instead of one 300 megawatt site, deploy 3,000 kilowatt pods. Puzzle pieces, not mega projects. Because the fabric is location flexible, schedulers can follow the sun and the wind. Route PyTorch jobs to green hotspots at 11 a.m., shift to night wind regions at 2 a.m. Treated as flexible demand, AI becomes a grid asset, not a burden. Absorbing surplus and backing off during peaks. That's how we scale sustainably. Here's the end-to-end architecture we can build together. Multi-tiered compute cloud data centers, edge pods, and personal GPUs in one open marketplace. Coordinator and scheduler. Shard tasks, assign partitions, orchestrate async gradient flows, and from PyTorch integration, custom process groups for WAN-aware, all reduce substitutions, and optimizer wrappers for local step accumulation. Compression and sparsity, and elastic job definitions for node joins and leaves. Verification and incentives, cryptographic spot checks with on-chain rewards. Train to earn, so anonymous nodes can be paid for correct work. Energy-aware routing, a cost function that includes grid carbon intensity and marginal kilowatt hours price. Send batches where the cleanest and cheapest. This isn't a rewrite of PyTorch, it's a new backend, new schedulers, and new market surface. Okay. Do have a little trouble with my clicker, but okay. Okay, why does this matter in this room? Because PyTorch developers are force multiplier. If we make it natural to select a distributor WAN, the backend we pick DDP today, we unlock frontier scale training for small batches and startups. We're not just reducing cost, we're expanding who gets to build. That aligns with the open source ethos that made PyTorch what it is. When we combine higher utilization, low-com algorithms, async resilience, and energy-aware scheduling, we see 3 system-wide wins. Utilization, more work per watt. Model quality, parity without waste. Cleaner AI, the fabric migrates to renewables as a first-class signal. So 3 messages to leave you with. AI's energy pitch is here. US data centers are using 176 terawatt hours in 2023 to about 325 to 580 terawatt hours by 2028. 6.7% to 12% of US electricity. If we don't adapt, energy, not algorithms, will be the bottleneck for AI. And distributed training works today. WAN-aware PyTorch training with 500 to 857 times less bandwidth. And with asynchronous resilience and verifiable incentives already matches centralized accuracy at relevant scales. We can turn idleness into intelligence. Build it into PyTorch, and new process groups, optimizer wrappers, and elastic schedulers, verifiable hooks, and energy-aware job routing. Make the internet a cluster, and we make clean energy a scheduling signal. The call to action for the PyTorch community is wrap your next trainer with local step accumulation and compressed sparse deltas measure the accuracy curve. Prototype an async parameter service using a gossip mesh with Nesterov corrections for stainless. Add verification stubs to your training loop. Commit to outputs you can prove. Expose a carbon-aware placement flag in your job specs. Steer work to the cleanest kilowatt. Together, we can build a distributed, resilient, inclusive AI infrastructure powered by clean energy and open to all. Thank you. Happy to take any questions. Sure.
Here you go. Thanks.
Yeah, thanks. I was curious, does dloco provide any sharding like FSDP, or is there any specific parallelism that works well for this kind of cluster?
So there is both data parallelism and model parallelism, right? For the dloco, I think it was data parallelism, but Pluralis has model parallelism, which is supposedly more superior because you don't need to replicate the data across all nodes.
Oh, cool. I'd love to see some newer like Mamba-style hybrid models trained using the cluster too.
Yeah, so Pluralis has recently announced an asynchronous heterogeneous node that you can plug in any 24 to 32 megabyte GPU. So they just released it last week, so I recommend you check it out. It's very, very interesting.
Cool. Thanks.